Hello. Hi there.
Hi, Beth. On my screen, it looks like you're pinned as you've got the spotlight on you. I don't know if that was deliberate. It may take a second or two for the tech folks to sort the panelists. Okay, I think that, here we go. Okay, and we'll give it just another couple of seconds for everyone to get sorted and organized. So each of our breakouts has a tech person who's working behind the scenes to make sure that we stay on track. And so it looks like it's coming together. Great. Okay. So I think we're all pretty well sorted. So I just wanted to welcome everyone to the Exploring Environmental Science and Nature-Based Climate Solutions breakout. And just a quick refresher about how this is all going to work. And this is very meta. It's a Zoom within a Zoom. So we're going to be here together until about 12:04. And then we'll get prompted again with another Zoom link, which will take us back into the main group for the final portion of our event this morning. And so what's going to happen here in this particular breakout is we're going to hear a series of 3 sets of presentations. They'll be between 10 and 13 minutes long, and then we'll have some time at the end for question and answer. And I think actually a couple of the presenter teams, we have academic and professional experts teamed with students in keeping with our youth theme for the day. Some of them are open to fielding questions on the fly. And so I know some folks were hoping to get questions in during the plenary sessions and we had the chat disabled, but that's not the case here. So if you have questions, feel free to type them into the chat and we will be monitoring them as we go along. And some of our presenters may choose to answer those questions kind of on the fly. And then we'll also have time at the end for answering some of the questions as well. And so I just wanted to go through the sequence of presentations. First, we'll have a talk given by Professor William Keaton and his student, Stephen Peters Collier. And then we'll turn the mic over to Dr. Charles Driscoll and his student, Qasim Mehdi. And then the final presentation will be from Britt Lundgren and her student partner, Morgan Irons. So I think I've covered all of the logistics, so I am happy to go ahead and turn over the floor to Professor Keaton.
Thank you so much for that introduction. Really wonderful to be here today and excited to talk about some really interesting and important nature-based climate solutions. So I am, okay, I think my slides are up. Perfect. So I am Stephen, and I'm going to be talking with Dr. Bill Keaton about forests and about how we can leverage forests to help with the climate issue and with climate mitigation. So I'm going to start off kind of basic here, going back to the beginning and discussing carbon. So carbon is, of course, a problem when there's too much of it in the atmosphere, but carbon is also essential to life and is naturally found on our planet in many places, or pools as they're sometimes called. It's found in the atmosphere, in forests, in soils, and the carbon is constantly moving between these pools. It's constantly in flux. It might move from the atmosphere to forests, from forest to soils, soils to the atmosphere. And this figure here looks kind of complex, but basically the main takeaway is that the carbon is always moving around from one pool to another. But the issue is that since we have burned fossil fuels, we have added a lot of carbon to the atmosphere, and this excess carbon is causing climate change. So what we're interested in is how can we take that carbon from the atmospheric pool and lock it up in forests? How can we store it in forests so it's not contributing to climate change? And how this happens really boils down to something that you may remember from high school biology classes is photosynthesis. So photosynthesis is basically how plants take carbon dioxide from the atmosphere and water and turn that into sugars, which they then use to make their structures, their tissues. And this is important for us because it means that plants take the carbon dioxide, which is the primary greenhouse gas, and convert it into their biomass. It means they're taking it out of the atmosphere and storing it in themselves. So this becomes important because it gives us a whole host of different natural climate solutions that we can leverage to help with the climate issue. Now, this is sort of a complex figure, and but the main takeaway is that on the left here is a list of all these different natural climate solutions. There's some involving forests, some agriculture, some wetlands, and the bars on the right show the potential that each solution has to mitigate climate. So a longer bar means there's more potential. And what's cool about this is that if the US was able to institute all of these solutions, they would be able to mitigate up to 21% of the net annual emissions of the United States, which is a big deal because as we discussed in the previous session, the US is a major emitter. So 21% is a lot of carbon. Now, when you look at this, you can see that agriculture has a lot of potential and forests as well has these very long bars. So there's a lot of potential to mitigate climate. And these solutions within forests, there's a number of different solutions. There's reforestation, fire management, a whole host of things. And so we like to say that there's a portfolio of carbon forestry options. And these can really be tailored to how one wants to use them, to public land or private land. And each of these solutions really emphasizes a different part of the process. So some solutions focus on young forests, and young forests, as they grow, as they add trees and as individual trees grow, they need to take a lot of carbon out of the atmosphere to grow. They sequester and uptake a lot of carbon and add it to the forest. So some solutions focus on this, what we call sequestration, or taking carbon out of the atmosphere. But as the trees and forests age, the forests start to store a lot of carbon because they're taking it out, and over time, there's just a lot of carbon stored. So other solutions in our portfolio focus on carbon storage, focus on really keeping the carbon stored on the landscape in the forests and not letting the forest get cut down and have the carbon go back to the atmosphere where it contributes to climate change. So we can break all of these solutions down into a couple of different groups, main kind of groups. So the first one is avoiding deforestation. Now this focuses on what I was just talking about, on keeping those forests on the landscape that already store a lot of carbon. And this, of course, stops the carbon from going to the atmosphere, which is great for climate change. There's a lot of co-benefits to avoiding deforestation. There's keeping these old forests around creates a lot of habitats for many species, has great recreational values. There's important traditional and indigenous resource values, among a whole host of other ecosystem services. In addition to avoiding deforestation, we can focus on reforestation. And this is basically adding new trees to the landscape. So this focuses on that carbon sequestration side of things, on pulling the carbon out of the atmosphere and storing it in these new growing trees and forests. And this has a whole host of benefits as well. Areas that are reforested along rivers are very important for water quality and flood regulation. Adding trees to urban areas is important for the urban heat island. And so in addition to avoiding deforestation and reforesting areas, we can also work on improving our forest management practices. And I'm going to turn it over to Dr. Bill Keaton to discuss more about this.
Okay, thanks a lot, Stephen, and thanks to everyone for having me here today. It's a pleasure. So the third category in our carbon portfolio, our carbon forestry portfolio, is what we refer to as improved forest management. And this is the one that probably has the greatest potential nationwide in terms of its relevance to working forests across a wide range of ownerships. Now, basically, it comes down to 2 or 3 key things. First of all, it means using efficient timber harvest scheduling or planning to slowly ratchet up the net amount of carbon stored on a working landscape over time. Secondly, it involves a whole host of innovative, ecologically friendly silvicultural practices or forestry practices, things like you're seeing here in these pictures, what we call retention forestry, where we basically retain more structure and more carbon in managed forests. And then finally, it includes things like extended rotations, basically allowing forests to grow for longer periods of time between harvests so that they build up and accumulate higher carbon stocking. So as Peter emphasized, the first of these three categories emphasize storage, the second emphasize sequestration, improve forest management, where we're actually seeing the lion's share of the action on the carbon markets, which I'll explain in a minute. Really combines both sequestration and storage. It's also very compatible with the production of large dimension timber, the types of products that are used in durable wood products that also comprise an important carbon sink. We can go to the next slide. And this one has been getting a lot of attention recently as people become excited for the potential to produce what we call structural timber or mass timber structures that might really store carbon themselves for long periods of time. This type of product also has what we call substitution effects, which means basically avoiding the emissions that would have happened from the production of something else, like concrete or steel or plastics, products that have a much higher carbon footprint associated with their production. So this is something to keep your eye on that we're probably going to see a lot of excitement around in future years. Okay, Stephen, next one. Okay, so hopefully you've gotten the sense that we have this portfolio of options for carbon forestry. It's not just one thing, not just a one-size-fits-all kind of deal. And each of these things brings a different suite of co-benefits that we can think about. And I've often liked to say that a forest that's well managed for carbon is probably providing a lot of other things that we care about. It's providing a diversity of habitats for wildlife and plants, and it's providing a lot of services that we depend upon, like hydrologic regulation and pollination services and open space and recreation, all of these things. So carbon, in effect, provides an umbrella for a lot of other things that we care about. Next slide. There are a lot of things that we could talk about, but one of the interesting things that we've really now shown to be true, so this is no longer just a working hypothesis, is that carbon financing for the production of emission offsets, which we can talk about in just a minute, has proven very effective at helping working forests to stay in business. It's an additional revenue stream that lots of landowners can tap into and can layer on all the other things that they need to stay in business. And this kind of carbon financing has been very, very helpful at conserving large, unfragmented working forests and what we call the forest blocks that are so important in northern New England for a whole variety of co-benefits. Again, open space, unfragmented interior wildlife habitats, hydrologic regulation, flood resilience, so many different things. So this is really a major co-benefit of carbon financing to think about. Next slide. And so as I just mentioned, there's this interesting connection between carbon and water that many people might not think of. It's not as intuitive as some of the others. And this has to do with the fact that structurally complex forests with complex architecture, also tend to have exceptionally high quality streams running through them. Just the sheer complexity of biomass and structure influences stream systems in a whole variety of ways and creates incredible diversity of habitats for aquatic biota. It helps with processes like uptake and processing of nutrient pollution. And even recently, scientists have shown that this type of stream has exceptional flood resilience value in terms of the ability of a stream like this to absorb and dissipate energy during flood events. So these are just a couple examples of many co-benefits that go along with carbon forestry. Next slide. And it's exciting then as we think about opportunities that rapidly developing carbon markets bring to incentivize this kind of work. Now, landowners in North America are looking at basically two different types of carbon markets. The first are what we call compliance markets, or cap and trade. And the biggest player in this arena is the California carbon market that landowners anywhere in the country can participate in. This has some advantages, like a higher price point, but it also has some disadvantages, like the fact that only single large properties are eligible for enrollment in the California market. So that works great if you own a big property, but it doesn't work as well for the typical New England landowner that owns a smaller property. There's also a longer commitment period of 100 years, which makes some people nervous. So a lot of people are looking at the voluntary market, which we also call over the counter, because of two things. One, it allows something called aggregation, which basically means multiple landowners pooling together their assets so that they gain the economies of scale needed to make a project financially viable. And then secondly, it has a shorter contract period of just 40 years. We have great experience now with a registry called the American Carbon Registry. So this works quite well for landowners in New England. And because the voluntary market, in which there's a buyer somewhere in the world purchasing emission offsets from a forest landowner somewhere else in the world, because co-benefits are such an important part of the story here, buyers are looking for carbon that tells the story of the place that it comes from, a landscape with exceptional wildlife habitats and open space values, iconic landscapes like we have in northern New England. We have the opportunity to generate what we call, or what I like to call, charismatic carbon. And these are offsets that truly command a higher price on the voluntary market. So we're well positioned here in northern New England to take advantage of charismatic carbon. Next slide, please.
Billy, you've got
and we've shown that this can work. Okay, so I'll just real quick plug a project that I've worked on with Vermont Land Trust and the Nature Conservancy called Cold Hollow to Canada. This is in north central Vermont, as you see here. And then Peter, the last slide, or Stephen, the last slide. And so we've pioneered, on the last slide, the Northeast's first large aggregated project on the voluntary market. I'm not seeing the last slide. If we could go to that one. There we go. So we've shown that this kind of aggregated project can work. We did this on over 8,600 acres, and we're now in the dissemination stage where we're sharing the lessons learned with landowners across New England. Okay, that's it. Thanks very much. We'll go to the last slide.
Okay, wonderful. Thank you both so much. And I did see a question in the chat, or someone is hoping to access your slides. And so I'm thinking that we'll figure out a way, if you are amenable, that we can upload those to the event website so folks can cruise through at a more leisurely pace. Okay, so we're going to turn it over now to Dr. Charles Driscoll and his student, Qasim Mehdi from Syracuse University.
Thank you, Anthea. Thanks again, everyone, for joining us in the Nature-Based Climate Solutions Breakout Room. My name is Qasim Mehdi. I'm a third-year PhD student at Syracuse University, and I study environmental policy. With us, we have Charlie Driscoll, who is Distinguished Professor of Civil and Environmental Engineering at Syracuse University. Dr. Driscoll is a man of many interests. His research focuses on biogeochem, environmental chemistry, and policy. In addition to that, he also carries out research which is widely published. He advises federal and state agencies and Congress and state officials. Today, Dr. Driscoll and I will be sharing two of our two research projects. First one models the emissions of number of different environmental policies over contiguous US. And the second is fascinating environmental experimental work, which Dr. Driscoll and his fellow researchers have carried out at Hubbard Brook Experimental Forest in New Hampshire. Dr. Driscoll, you have the floor.
Okay, thanks, Qasim. Well, it's good to be able to participate in this session. So as Qasim said, we're going to talk about two things. The first is we're looking at different policies, the impacts of different policies, the cost of these policies on the electricity sector to reduce carbon management. So we've looked across a wide range of different types of approaches, and these approaches include existing regulatory proposals that have been floated in previous administrations, Obama administration and Trump administration, and then a suite of other types of policies known as clean energy standards, which set a benchmark for emissions, cap and trade programs that you heard a little bit about in terms of the carbon markets for forestry, but to try to provide a cap and provide opportunities for trading. And then finally, a carbon price, putting a price on carbon. And so we're going to show you some broad output from these different policies. So the way we do this analysis is we use a variety of models. The first model we use is sort of an economic model called the integrated planning model, that we were able to determine the cost. This is at a national scale, so this is for the whole US. It also, from these different policies, we get projections over different time periods of different emissions, not only carbon emissions, but also co-pollutants, traditional air pollutants, such as sulfur dioxide, nitrogen oxide, mercury, that can contribute to air quality problems. We then apply those emissions to an air quality model, a comprehensive air quality model, to look at air quality projections. And then we take those air quality projections and put that into an epidemiological model or an ecosystem model to look at effects on ecosystem or human health. So I just want to show you some sort of broad trajectories about reducing carbon from these various policies. You see two slides here. One shows the changes in carbon emissions through time for these various policies compared to a business as usual. And one of the policies, which is the Trump administration policy called ACE, which is shown in orange, and the business as usual is shown in green. And that compares to the overall cost. So the cost of business as usual compared to these additional policies. So you see a whole variety of policies, and they show different trajectories. But the bottom line is that a vast majority of these policies can reduce carbon emissions at relatively modest costs over a relatively fast time frame. And that's really good news. As I said, we put that information into an air quality model, and so that we can look at what are the projections in critical air pollutants like fine particulate matter and ozone. And these are shown a couple of slides showing the business as usual scenario for particulate matter and what could be the reductions for one of these aggressive policies, where the greater the green color shows the greater the reduction in these critical air pollutants. And then Qasim puts this into an epidemiological model to look at health benefits associated with this. So these are two maps showing lives saved per year for 1 year, 2030, due to these air pollutants, fine particulate matter and ozone, for two clean energy standards, one that involves banking, which is on the left, and one that doesn't on the right. And so you can see there are large numbers of projections of lives saved. For the banking projection, it's over 11,000 lives saved per year. And for the non-banking, it's almost 6,000. And you can see that this is color-coded by county. So the greater the dark blue, the greater the numbers of lives saved in a particular county. So one of the things that we want to touch on here is environmental justice issues. And I think it's important to point out a few things. First of all, for some of these air pollutants like fine particulate matter, there is no safe concentration in air. There are benefits down to very, very low concentrations. The other issue is that we all don't breathe the same amount of air. Different demographic groups are exposed to different areas, different amounts of air pollutant, which is shown in this slide here. So you can see different demographic groups experience greater or more severe air quality than other groups, and that has significant health benefits. So for the first part, I'd like to summarize quickly what we've learned from this activity. And if you're interested in finding out information, we can get that to you. So the first thing is that all of these policies produce net benefits. In other words, the benefits associated with climate and health exceed the costs. Number two, there are many policies that are able to produce low or zero emissions by the time scale of 2040 to 2050 at modest costs above baseline, only 15% above what we would be expected to spend if we did nothing. So that's great news. In addition, there's a number of modest policies that can achieve large emission reductions, but even at lower costs, only about 9% above baseline. And then finally, the design matters. The design, we have different outcomes depending on the design, and that's something that we're going to have to debate as we move forward with these policies. So I'm going to hand it back to Qasim, and he's going to ask a couple questions.
Thank you for those slides, Dr. Driscoll. My first question is that if you were President of the United States of America, which policy would you pick and why? Do you think your preferred policy option is feasible in current political atmosphere? And perhaps I'd like you to touch a little bit on the policy design as well, for that policy of your preference.
Okay, well, those are good questions. I don't think I'd ever be in a position to be president, but I think it's going to be a huge challenge to move forward on these, and that's why I think it's good to look across a variety of possibilities. If I was king, I would pick the most ambitious policy because, first of all, I think it's extremely cost effective. The benefits greatly outweigh the costs. And I think climate change is a huge challenge. We need to get on it right away. And I would go with the most aggressive policy, but I'm a realist as well. And so that's why I think a range of policies are useful. Some of these have very modest costs and can achieve a lot of reduction. So the big thing we could do is get rid of coal. I cannot emphasize that enough. The air pollutants associated with coal are disproportionate compared to the other fossil fuels. So that should be the #1 priority. We could, with some of these policies, we can do that by 2030 and produce good jobs with alternative energy sources and have a tremendous health benefits. So I'm going to shut it off there because we're running short on time. Do you have another question?
Yeah, sure. I can actually connect it with your previous answer regarding coal. If we are phasing coal out, there are going to be losses in jobs, maybe in West Virginia or coal belt. So are there any distributional effects on the economy?
Well, there are clearly distributional effects, but I think there are good opportunities for, as we talked about, for a clean energy economy, for new jobs. I frankly think that we've lost a lot of those coal mining jobs back in the 80s and 90s because the industry is highly mechanized today. So I think that there are people who have jobs, and that is a significant issue. And I think we have to work on training of those individuals and transition them to a clean economy, because I think the benefits are tremendous, and a great number of people could benefit from this transition. So Qasim, maybe we should move on to the second part.
Yeah, I think that sounds like a good idea.
Okay, so Anthea, our host, suggested strongly that I talk a little bit about Hubbard Brook. I've been working at Hubbard Brook, and it's, as she said earlier, it's an experimental forest in New Hampshire, shown here. It's a long-term study. We have long-term measurements which inform our understanding of climate change and changes in stream flow and quality, as Dr. Keaton talked about. There's a number of experimental watersheds within Hubbard Brook, and within those we are able to do different experiments. We've done a number of experiments on forest harvesting management. We've also done another experiment that was a little bit different, and that involves addition of calcium in the form of a calcium silicate mineral to try to mitigate the effects of acid rain. So this is something we started in the late 90s, and we implemented it. So what we did was we contracted with a mining operation to mine this material, ground it down to a very fine material, on the average about 10 microns. It was pelletized, and then we applied it by helicopter to about a 10-hectare watershed at Hubbard Brook. The idea behind this was to try to mitigate the impacts of acid rain. And indeed, it was wildly successful. But it's interesting, there's a group from the UK who contacted us a few years ago and said that, did you realize that within the Paris Accord, there are incentives to try to study amendments and the impacts of amendments on as helping to mitigate climate, and silicate minerals are one of those amendments. And they said we were the first person in the world who'd actually done this thing, and they wanted to study and model the climate impacts. And so what this does is, as these materials break down, they enhance the sequestration of inorganic carbon from the atmosphere and have it go into stream water, which then gets permanently sequestered within the ocean. So we found indeed that this was going on at this site, but also this site enhanced above ground biomass production. And so we saw not only did it enhance the growth of trees, but it also enhanced the sequestration of inorganic carbon from the atmosphere. So it was sort of a twofer. So anyway, Qasim, do you have any questions on this?
Yes, I do. Dr. Driscoll, walzenite, this calcium-based mineral, not only captures carbon from the environment, the atmosphere, but it also helps in the forest growth. So great things. How do you feel about sprinkling walzenite, say in the Appalachian Mountain, all over it? Seems like an interesting strategy to preserve our forests, grow them, and also capture carbon.
Yeah, I think it would be a challenging program to implement, because as you say, can you imagine, we've got a lot of protected lands all over the Appalachian Mountains. Can you imagine a suite of helicopters flying over all the time, dumping chemicals? I can imagine that the pushback there would be even more challenging than to implement a carbon management program from the electricity sector. So I think it's an interesting idea, but I think it might be hard to implement in forest lands and natural lands. It might be easier to implement within agricultural systems that normally apply fertilizer. So I know we're running out of time. I think we should cut it off and move it to the next group. But thank you, Qasim. Great job on your questions.
Thank you so much.
Thank you both so much. You're perfectly on time. And folks who are listening in, the participants, don't be shy. Feel free to post your questions in the chat, and we'll have an opportunity to scroll through those and answer them at the end of the presentation. So we have one more set of presentations to go. Britt Lundgren from Stonyfield Organic and her student partner, Morgan Irons from Cornell University.
Okay, wonderful. So I'm going to introduce myself first, and then Britt will introduce herself. And then we'll go into a series of Q&A where we will be asking each other questions on this topic. So hi, everyone. My name is Morgan Irons. I am a soil and crop sciences PhD candidate at Cornell University working with Dr. Johannes Lehmann. I'm also an NSF Graduate Research Fellow, a Norfolk Institute Fellow, and a Carl Sagan Institute Fellow. At Cornell, my research focuses on understanding bacterial adhesion mechanisms in organo-mineral surface interactions in soil aggregates and their effects on soil organic carbon persistence across different soil types, land uses, and gravity conditions. So my work not only takes me into agricultural and ecological systems here on Earth, but also to the International Space Station, where this last year we've sent the first natural soil samples and biochar samples ever sent into space, which is really cool. The results from our ISS experiment, as well as our Earth-based experiments, will provide us with a better understanding of fundamental soil biogeochemistry dynamics here on Earth and how to better hone and implement wise soil management practices. Soil management practices under different land use conditions not only directly affect overall soil health, such as fertility and crop productivity, but also impact agricultural greenhouse gas emissions and the ability of farmers to buffer the impacts of climate change. Finally, to close out my intro, I am not only a graduate student, but I am also the co-founder and chief science officer of the space and agricultural business, Deep Space Ecology, which works to solve the challenges of food insecurity and problems of human sustainability in the deep spaces of Earth, the Moon, Mars, and beyond. So with balancing a PhD and being a business owner, I keep myself busy, but it also provides me with a very unique perspective on how we can use science, fundamental science, and feed it into field and community applications and vice versa. And now I will turn the floor over to Britt.
Thank you, Morgan. Hi, everybody. Thanks for joining us here today. I don't have slides to share, but I'm just going to talk briefly, bringing us back to earth a little bit here, talk briefly about Stonyfield's commitment to sustainability and how this has led us to focus on land-based climate solutions, particularly in agriculture. Stonyfield's been working on sustainability for a long time. We got our start as an organic farming school, and yogurt was actually just a way to bring in funds to support the school. But over the years, we decided to focus on the work on the yogurt, and our work has really focused in on reducing greenhouse gas emissions. And, we've pioneered things like full scope carbon footprinting for businesses. We were one of the first businesses in the US to do that. And we were also the first US manufacturer to offset all of our emissions from energy. 2 years ago, we decided to refresh our emissions reductions commitments, and we set a science-based target. And our goal is now to reduce our emissions full scope 30% by 2030. We know that over half of our emissions come from agriculture, and so a big part of this strategy is focused on reducing agricultural emissions, and particularly focused in on the opportunity around soil health. We are really excited about this opportunity on soil health because we see it as a powerful tool to increase carbon sequestration, but we also see it as being extraordinarily beneficial to farmers who engage in this work, because when they improve soil health, they improve their resilience to extreme precipitation events, which we're seeing more and more of here in the Northeast. And they also improve their resilience to drought, which we dealt with in a pretty serious way over the last growing season. So we're excited about soil health because it's really one of those win-win solutions that we're all always looking for in this field. And we know that organic agriculture brings benefits in and of itself. So we know that organic soils sequester about 26% more carbon on average than conventionally managed soils do. But we also know that every farm has room for improvement, including organic operations. And we've really focused in on finding the best ways to monitor and measure soil emissions. And so this has led us to launch a platform together with Wolf's Neck Center for Agriculture and the Environment in Maine. The platform is called Open Team, which stands for Open Technology Ecosystem for Agricultural Management. And it's designed to link together the tools that are used for measuring and monitoring soil health on the farm in a way that makes it easy for farms to manage their information through these tools, to move their data and take advantage of it so that they can get back site-specific recommendations for what they can be doing to improve soil health. And then they can verify those results using the tools in the platform. So we're really driving towards an efficient way for farms of all types and sizes to engage in improving soil health, reducing emissions, and hopefully participating in emerging carbon markets, whether that's federal incentives or whether these are private markets that are coming together. So we're currently trialing these tools with about 10 of our organic dairy farms that ship to us. And if we're successful, we'll then work to bring all 250 farms that supply our milk into the program. And we believe that if we can achieve a rate of about a ton of CO2 equivalents per acre of sequestration, that we can actually offset about a third of Stonyfield's total greenhouse gas emissions. So we could actually achieve our entire science-based target just with soil carbon if we really knock it out of the park. There's a lot that needs to happen to actually get there, but that's the vision that keeps us going on this work every day. So we're going to shift now. Morgan and I are going to ask each other some questions, and I'm going to start, Morgan, with a question for you. If you can just say a little bit more about your work and how you look at soil addressing climate change, and what do you see in the work that you're doing in terms of the opportunity in this area?
Yeah, so, well, when we think about how soil plays a part in addressing climate change, one of the roles that soil can potentially play is to help mitigate greenhouse gas emissions and sequester carbon dioxide from the atmosphere by plants as carbon in the forms of soil organic matter and organic carbon. And soils contain the largest pool of terrestrial organic carbon here on Earth. And when I say soils, it is important to clarify that carbon concentrations, stocks, losses, accrual rates vary spatially across soils due to differences in the land uses, the soil mineralogy and texture, local and regional climates, plant species, soil biodiversity, etc. So knowing this, the capacity of soils to sequester carbon and the way we manage soils and soil carbon can be site-specific. In agricultural systems specifically, the main greenhouse gas emissions that we see are carbon dioxide, methane, and nitrous oxide. And this is not only due to soil management, but also livestock management, land cover change from harvesting crops across the growing season to converting forests, grasslands, wetlands into agricultural land, as well as the degradation of landscapes over time. You might have heard of the phrase climate smart soils. In this area of study, there is research being done on understanding soil carbon sequestration and storage processes and how the use of different soil management strategies affect greenhouse gas emissions. The implementation of these activities is still pretty early stage, and there are still key knowledge gaps and challenges that scientists are working to figure out, some of which require the improvement of predictive models, high resolution field measurements, quantifying uncertainties. There's quite a bit of work to do. My work at Cornell looks at one of the fundamental knowledge gaps we have in understanding soil organic carbon storage and persistence. In this case, questions surrounding mineral surface interactions with organics and microorganisms in soil aggregates and how these interactions affect soil organic carbon persistence. My research is mainly focused on improving soil health, which you talked a lot about, Britt, which we need to do, and it needs to happen no matter what. Soil health is very, very important, and it can help buffer systems against climate change impacts. But due to the nature of my research as well, it is also contributing to building our knowledge on how carbon can be sequestered and stored in soils. Now, you pretty much answered a few of my questions in your intro. It's all good. So let's see. So prior to joining Stonyfield Farm, you worked as an agricultural policy specialist for the Environmental Defense Fund. How did you go from working policy to being the director of organic and sustainable agriculture at Stonyfield Farm? And has your work in policy shaped how you approach climate change mitigation goals at Stonyfield?
Yeah, so I have an interdisciplinary background in agriculture science and policy. I have a master's degree from Tufts, and I pursued policy after graduate school partly because of timing. The Farm Bill, it ended up being the 2008 Farm Bill when it finally passed, but the Farm Bill was getting moving, and so there was sort of opportunity to jump in and work on farm policy with the most important piece of legislation that we have. And I was fortunate because as the Farm Bill was wrapping up, the debate on cap and trade legislation was really starting to move along. This was the Waxman-Markey bill in the House back in 2008. And I was able to transition to working on the role of agriculture in that bill. And so it gave me a front row seat to see the interaction of the agriculture community with the dialogue around climate change, which has really changed radically since then for the better. So back then, the Farm Bureau and other major commodity organizations were all in lockstep opposed to cap and trade legislation because they saw it as a way that agriculture was going to be regulated, and they didn't see a potential benefit. And I think since then, farmers have really come to see that both that they're being impacted on a routine basis by climate change, it's hurting their profits, but also that there's an opportunity here for them to become a part of the solution. And I jumped at the opportunity to move from DC and come to Stonyfield. In part, I wanted experience in a different sector. I wanted to be working with farmers in the Northeast where I'm from. And I love that it gives me the opportunity to sort of take a systems approach to this work. I continue doing the policy work. I'm engaged in government affairs and advocating for climate legislation a lot these days. There's a lot happening. But I also get to see like what this work actually looks like in action on the ground as farmers try to address climate change. And so I feel like it gives me a really practical perspective on what farmers are willing to do when it comes to engaging on this issue and what's possible and what the technical challenges really are. And at Stonyfield, we work with smaller producers on average. The average herd size for our dairy farms is 75 cows, which, you know, I mean, most milk that you get and conventional milk that you get in the grocery store comes from farms with over 10,000 cows these days. So we're talking about much smaller operations, and they need different kinds of tools and different kinds of solutions than those larger operations do. So I feel like I'm able to take a systems approach to my work that allows me to be more effective in the long run, I hope.
Britt and Morgan, I'm going to just jump in to let you know that we're running out of time, and I wanted to go ahead and address some audience questions if that's okay with you. We only have about 5 minutes left, and what's going to happen is the people who are managing, the tech gurus behind the scenes, are going to drop the link back to the main meeting in the chat. And so that'll happen in maybe about 4 minutes, and that'll give us 1 minute to get settled and reoriented back at the main meeting. And so I just wanted to open up the floor to any questions in the chat. I saw that there was an exchange back and forth between Eric and Bill Keaton about tree stumps. And I don't know if you wanted to unpack that for the rest of us while other questions come in, if there are any.
Well, maybe I'll just say really quick, I appreciate the question. I mean, I think that it speaks to some of the details involved in these silvicultural practices. And, you know, Eric, I think that basically anything that you can do to maintain carbon on site, you know, over the course of multiple management rotations, that includes things like stumps and roots and soil carbon and all kinds of structures, the more carbon you retain and store in the system. And that's what we're talking about with all this kind of forestry. It just gets tricky when you try to generalize about specific systems or approaches, because forestry is never that easy. It's always, you know, complicated by so many factors and variables that you need to consider. But I appreciate the question.
Okay, thank you so much, Bill. And I'm scrolling through the chat here and I see another question from Eric. He says, thank you. I also have a question for Britt. I'm wondering if you could speak more to the methods being used at Stonyfield to mitigate or neutralize your impacts and how those methods are implemented and monitored and measured. It's kind of a biggie, and the clock is ticking.
Well, we use life cycle analysis to understand where emissions are coming from across all of our activities in manufacturing, transport, packaging, agriculture, et cetera. And then we have 5 different strategy areas where we've identified what we think are the most feasible and the most important areas of emissions to address. So that spans across energy usage, packaging, waste, logistics, and then agriculture, of course, which we're focused on soil health there. It's a lot to cover here, but we do actively measure in all of those spaces so that we're, you know, not just trying things and hoping for the best.
Okay, I appreciate that. And I know that these are very intricate, complicated questions and issues, and it's hard to do them justice in such short time. And so now that I said that, I did see earlier in the chat a question about biomass, and I don't know if the panelists got a chance to see that or if anyone wants to take a stab at biomass. So the question was from Peggy, and it was hoping to hear something about biomass for power and the feeling that it's very damaging to the nature-based solution approach in temperate forests. And what do you think is the best way for tackling this problem? In 2 minutes, anyone want to take a stab at that? Charlie or Bill, maybe.
Charlie, do you want to, or shall I?
Go ahead.
Okay, well, Peggy, I mean, you've touched on one of the thorniest issues right now in the forestry field that is really actively under debate, and you're going to find all kinds of different opinions on this issue. My lab actually has done quite a bit of research on this, trying to understand the greenhouse gas emissions consequences of different types of wood biomass energy And it's like one of these things where the devil is in the details. You know, it really depends specifically on how the wood is harvested, and again, how much carbon we maintain in the forest itself. It depends on what kind of fossil fuels we're substituting for, like coal versus natural gas. It depends on the specific energy application, like are we talking about large biomass plants, combined heat and power, or are we talking about high efficiency, municipal or home thermal applications? So the mission consequences are really different depending on which of those you're talking about. And so the answer is one of these really unsatisfying, it depends. It really depends on the specific scenario. But I think as a region, we're moving really aggressively towards wood biomass energy. And that's something to maybe be a little bit concerned about, because it really does depend on exactly how we do this, and we want to do it right.
Thank you, Bill. Okay, I think we really only have another minute or so, and then we can expect a link in the chat to take us back to the main meeting and for our final conversation. And there it is. Last thing I wanted to say before we all zip off to the main meeting is one of the most interesting aspects of planning this day was getting to talk to the people on this panel right now as we were kind of hatching a plan for what we wanted to say and how to coordinate. And I think it was an insight from Bill during one of those planning conversations about how we might be able to collaborate across sectors, agriculture and forestry, in order to learn from one another. We're all kind of trying to achieve the same goals, but maybe using different approaches and different techniques. And so the opportunity to harmonize, and we're starting to do that today with this conversation, seems really important. And so looking forward to continuing those conversations. And I just want to thank the panelists, again, the students and the experts, for a really fascinating and lively conversation. So thank you so much. And if you go ahead and click that link, we'll be whisked back to the main meeting. Thank you.
Thanks very much.